All right, welcome back. Today we're going to talk about a slightly different type of limit. Okay, so in the previous video we talked about the behavior of the function. Here, let's write it down fast. We talked about the behavior of the function x squared minus 1 over x minus 1. We said the limit as x went to 1 of that function we said was equal to 2. We examined the behavior from the left, behavior from the right, and they were all equal to 2, which implied that behavior of the two-side limit was also equal to 2. Now, that was the behavior, was the limit as x approached a finite value. Obviously 1 is a finite number. We're approaching 1, and that's a finite number, okay? But there's another type of limit, and you heard me mention this, and I said we would explore it in a future video, so let's go ahead and take care of it. A limit can also be thought of, or just a different type of limit, is a limit that it not examines the behavior of a function as we approach a finite value. We call that value c. So we're not approaching a finite value c, but we're approaching either positive infinity or negative infinity. That is, we're concerned with the behavior of the function as the function, we say, increases without bound or decreases without bound. As the x values get really, really big and positive, or really, really, really big and negative. So the behavior here, we look at, as x is 10 or 100 or 1,000 or 10,000 or 100,000 or a million. We're saying what happens as those x values get really, really, really big, as they get astronomical, either positive or negative. So again, what I call this is the, well, I would say this is the limit. This table is going to give me the limit as x approaches infinity. And this table over here is going to give me the limit as x approaches negative infinity. We call this x increases without bound. Sorry, as x, this is decreases because we're going to negative infinity. As x decreases without bound. And for as x approaches infinity, we'd say this is as x increases without bound. So this is just a different way to think about a limit. It's called a limit at infinity. These are called limits at infinity. And we're interested in what's happening, way over here on the x-axis, or way over here on the y-axis. That's what these are doing for us. They give us end behavior. Specifically, these limits are going to give us horizontal asymptotes. We'll talk about that in just a sec. Let's first consider the graph, and then we'll talk about the table as well. So notice what's happening here. So here's our function. It's kind of a crazy function. 3 minus 2e to the negative x divided by 1 plus e to the negative x. But I provided us with a graph, and we'll use a table as well. What do you think is happening, as we, here I'll break the axis. Whenever you see an axis that's kind of like gets jagged like that, that means we're breaking it. So instead of counting by twos all of a sudden, now we're going to say, I don't know, let's do like 1,000. And then, I don't know, 100,000 or something. Like something crazy. What do you think is happening way over here? Well, to me, it looks like the trend is that this function turned horizontal, or maybe not completely horizontal, but basically turned horizontal, and then I think that trend is just going to continue. That the function basically turned horizontal, and the way the arrows mean basically continue that behavior. So continue that behavior of basically going horizontal, to the right and here to the left. So what do you think that means as far as the function values are concerned? Well, if you use a table of values, I mean, my guess here would be that this function is getting closer and closer to this y value. Here, I'll put some dashed lines in here. This is really, really, really close to 3. And down here, we are really, really, really close to -2. Okay? And that trend appears to continue forever to the right as x increases without bound, and forever to the left as x decreases without bound. And if you want to use a calculator real fast, we can probably use a calculator to do some of this. Now, sometimes a calculator conks out whenever you're using really big values of x, but we can maybe use it for a couple of these at least. So let's see, that's our last problem. We need to type our new function in now. Let's see, so our new function is right here. Again, use parentheses always if you have a quotient. 3 minus 2 e to the negative x. And then close the parentheses around the numerator. Divide by 1 plus e to the negative x. Close parentheses. Let's double check all that. It's good. Second quit. And now if we go to our table, we can go and quickly get these function values. Now let's see. We want let's do as x increases without bound first. So these are the positive x values. 10. Let's do 100. Let's do 1,000. Let's do 10,000. Well, let's do 100,000. And 1,000,000. And what do you notice is true about all those y values? At first you can see at 10 it's really, really close to 3, but not quite there. But in fact, I mean, if you round, let's see, if you round to 1, 2, 3, 4, 5, if you round to the 5th place or less, you get 3. So I'm just going to go ahead and call it 3 because that's so close to 3. I'll say maybe approximately. So because it's definitely not equal to 3. Maybe let's say approximately 3. And then notice again for the rest of the x values, the calculator just went ahead and rounded it to us. Now let's be clear, it's not exactly 3. But the calculator is saying, hey, these calculations are so big, we're just going to go ahead and round to 3, is what the calculator is doing there. But it is some number that's very, 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 very close to 3, actually smaller than 3. It'd be like 2.99999999999 or something crazy like that. So we're going to say, for all of these, the answer is approximately 3. So what do you think that tells us as far as this limit is concerned? The limit is x goes to infinity. In fact, let me go ahead and put in the exact limit definition that we know it is. So it's 3 minus 2e to the negative x over 1 plus e to the negative x. So this table of values confirms our picture and tells us as the x values get really, really, really large, the y values are basically static. Not exactly, but they're really, really, really close to 2. And really, really close to 3, and just getting closer and closer to 3. So the limit is 3. That is, remember our definition, my very informal definition, that the y values are just getting closer and closer and closer and closer to that 3 means the trend. The trend in the y values as x goes to infinity, the y values just get closer and closer to 3. That's why I like my trend definition, my very informal definition, that the trend in the y values is the y values are simply really, really close to 3. Now, what about on the other side? On this other side, it looks like the trend is that the y values are just getting really, 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 really close to -2. Let's see if we can use a table of values to determine this. Now, the calculator might not like me on this one. Let's see. So if we type in, -10, let's see, 10, and then enter. Okay, not so bad. Start with -100. Not so bad. -1,000. So it's still working. I bet it's going to stop working here soon. Okay, yeah. Okay, so I bet it's going to give me error for the rest out. So that's going to be -100,000. Let's see. 1, 2, 1, 2, 3. Yeah. And then -1,000,000. 1, 2, 3, 1, 2, 3. Yeah. Now the reason it's giving me those error messages is because basically the calculator is having a hard time calculating E. If I plug in -1,000,000, notice that it'd be a double negative on both the positive, the numerator and denominator, and the calculator is having a very hard time handling that. You can get an online calculator to do it, but I mean it's really no use here because we see what the trend is. You plug in -10, -100. And let's talk about this again. So it's not exactly equal to 2. So let's hover over here and see. So the calculator says 2, but it's actually, notice again, it's like really, 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 really close to -2. It's actually a number a little bigger than -2, which makes sense looking at our graph. The graph is actually above that horizontal line at -2, but it's getting closer to -2. There's this asymptotic behavior going on. And let's see. When we plugged in a -100, the calculator said I can't do it. I'm just going to round it. But that makes sense, right? Because that's so close to -2 already. If we round to the 1, 2, 3, 4, 5, the 5th decimal place again, we're gonna get -2. So we can say approximately equal to -2. Approximately equal to -2. Approximately -2. Approximately -2. Approximately -2, and approximately -2. Okay? So our behavior is that those y values, as the x values are getting very, very, very big and negative, the y values are just hanging out down here at -2, getting closer and closer and closer to -2. So we would say, in terms of a limit, that the limit as x goes to -infinity of the function 3 minus 2e to the -x over 1 plus e to the -x, we would say that's equal to -2. So the limit as x decreases without bound, or the limit as x approaches -infinity, those mean the exact same thing. We have a limit equal to -2. Okay? And then going here, we can see that graphically, this means there's a horizontal asymptote at -2 and at +3. Now, we'll talk more about horizontal asymptotes in the near future, but it turns out that a function can either have 2 horizontal asymptotes. Why? Because there's 2 possible limits at infinity. You have the limit as x approaches positive infinity, and you have the limit as x approaches -infinity. Those 2 limits can both result, if they result in a finite number L, well then you get a horizontal asymptote. So you could possibly get the same limit in both cases. In that case, you'd have one asymptote. You could get different numbers like we did here, -3 and +3 and -2. We got 2 different finite numbers. We have 2 different horizontal asymptotes. And then you could, turns out, get no limit at all, or one but not the other. So it's possible that you could have 2 horizontal asymptotes, 1 horizontal asymptote, or 0 horizontal asymptotes. And do remember the equation of a horizontal asymptote is y equals the y value. So in this case, we would have a horizontal asymptote at y equal +3 up here on the top right, And in the bottom left, we have a horizontal asymptote at y equal -2. So that's just a little algebra refresher for you. That's how you write the equation of a horizontal line, therefore a horizontal asymptote. The definition of a limit at infinity, and again, this is like kind of an informal definition, but it suffices for us in a first semester calculus class. Let the function be defined on an open interval from a to infinity, and we say that if f becomes arbitrarily close to a finite value L for sufficiently large values of x, then we write the limit as x increases without bound as x approaches infinity of f of x equals L. Okay? And again, if you want to think about this for the negative infinity, we could replace that with negative infinity to a like so, and get a definition for negative infinity. That's just the analogous situation. Okay. So that's limits at infinity. We'll have many more examples of how to figure out limits at infinity, using different techniques, whether it be graphical or numerical or whatever. But that's an introduction, at least, to a limit at infinity. Okay, so we explored the solution via table, and a graphing calculator didn't really help us out that much. It helped a little bit, for this case, but for the negative infinity case, didn't really help us much because the calculator can't handle really big values of x. But no worries here, because we had a graph to work with, and being able to find limits via a graph is a very important skill. So we have the graph, and we can see that the y values, as x approaches positive infinity, the y values are getting super, super close to 3. And as x approaches negative infinity, the y values are getting super, super close to -2. Therefore, we had our two limits at infinity. These are both referred to limits at infinity, as opposed to the example in the previous video was a limit as x approached a finite value, which in some sense we call that just a regular limit. Limits at infinity, or we'll always be sure to specify that's something a little bit different, but the same concept is true of a limit is a trend in the y values, in the function values. Okay? I'll catch you in the next video. If you have any questions, always feel free to reach out. Until then, have a good one.